Now we've looked at the natural exponential function and how to differentiate it. Now we're going to look at the derivative of the natural logarithmic function, and that's ln x. Now ln of x can be written as log to the base e of x, and it is the inverse function of our natural exponential function e to the x. And on the diagram in blue is plotted y equals the natural exponential function of x with the key points 0, 1 and 1e marked on. If we reflect y equals e to the x in y equals x to get the inverse function, we get y equals the natural logarithmic function of x with the key points 1, 0 and e1. Now, as that function tends to negative infinity, it gets closer and closer to x equals 0, but it never reaches there, and it never becomes a negative value. So that's why we use the modulus lines on either side of our function, because our function of x always has to be positive in order to be able to take the natural logarithmic function of it. So we said that these are the inverse functions of each other. So if we take f after we take the inverse function of f, we know that we're going to get x. So if we substitute in our exponential function to the power of our natural logarithmic function, we're going to get that equaling x. We also need to remember that ln dot e equals 1 for when we're simplifying our functions. So there are two ways to derive the derivative of the natural logarithmic function of x. The first way is to say that if y equals ln x, then we can rewrite that as x equals e to the power of y. Now we want to differentiate this, but we're going to have to differentiate with respect to y instead of with respect to x. So the derivative of x with respect to y is going to give us e to the power of y. Now, this behaves like a fraction, so we can take the reciprocal of both sides. So we're going to get dy by dx equals 1 over e to the power of y. Now, if we go back up to the top, we said that x equaled e to the power of y, and we want to represent our function with respect to x. So our final step is to say that dy by dx equals 1 over, and we're replacing that e to the y with the x, so it's 1 over x. The second way to derive this function is to start with that inverse relationship. So we're going to start with e to the power of ln x equals x. Now we want to differentiate both sides of our equation. So we're going to say that the derivative of e to the ln x with respect to x equals the derivative of x with respect to x. Now we're going to use the chain rule to differentiate that e to the power of ln x, and we're going to get e to the power of ln x multiplied by the derivative of that function ln dash x. And the derivative of x with respect to x is just 1. Now we're going to divide both sides by that e to the power of ln x, and it's going to leave us with our ln dash x, or the derivative of our logarithmic natural function, and that's going to be 1 over e to the ln x. Now again, if we go back up to the top and look at the fact that we can represent e to the power of ln x as x, we can then rewrite this as the derivative of ln x with respect to x equals 1 over x. Now this is given to us on our advanced higher formula sheet, and so the standard derivative f of x equals the natural logarithmic function of x equals f dash x is 1 over x.